Hello, everyone. Welcome to today's Distinguished Warring Seminar. It's my great pleasure to introduce today's speaker, Dr. Brett Murray. Dr. Murray is a professor of geomorphology and coastal processes at Duke University. And he also serves as a director of graduate studies in the Nicholas School of the Environment. He's a leading geomorphologist, study a variety Earth surface processes in a variety of environments, including rivers, coastal environment, desert, and the Arctic environments. And he combines very elegant numerical simulations and observations to study the coupling between the complex physical processes, ecosystems, and human activities. And a very exciting and proud fact is Dr. Brett Murray actually got his bachelor's and master and a PhD here at the University of Minnesota. So we are very proud to have you back. And today he's going to talk about large-scale coastal morphodynamics and anthropomorphodynamics. So without further ado, the floor is yours.
Thank you very much. Thank you for the kind introduction, Judy, and thank you for bringing me here. I'm really, really thrilled to be back and get to talk about some what I consider fun stuff. And just to start with, the image here is a space shuttle picture of the North Carolina coast, and this is going to be a case study for a lot of the things I'll be talking about, both for the morphodynamics, which just means when a surface or a landscape determines the patterns of sediment flux that in turn reshape the landscape. That's morphodynamics. This is also a nice case study for the human component of this system, because parts of this system, that third cape down there, Cape Fear, is very heavily developed up to about here. And a lot of this is protected land, mostly national seashore, which is our coastal equivalent of a national park. There are a few towns grandparented in, and they're all connected by a really important transportation corridor, mostly a highway that will come up later in the talk. And please stop me along the way with questions. So it's going to be two parts. The first one is going to focus on the plan view shapes and how those come about and how those change over time. The second is going to bring in the vertical dimension and talk about cross-shore profile dynamics and how these coastal environments tend to keep up through some feedbacks with sea level rise. In both parts, I'll also talk about couplings between human and natural dynamics. And this is just going to be a sampling of work done with a bunch of wonderful colleagues over the years. So I'm happy to get to be the one to show it all to you, but this is work of many. All right, so on the first part, for the plan view morphodynamics, we're going to be purposely ignoring a lot of things that are really important on relatively small space and time scales, like storm dynamics and cross-shore transport, which we'll come back to some degree in the second, which we'll come back to in the second part. But here, what's really important for the long-term shaping and changing of these, the coastline location, is along-shore sediment transport. And so first, some introduction on what that is. This is all wave-driven transport of sediment, sand, gravel, boulders, whatever you've got on the beach, along the shore. And this happens just because of wave momentum. So this is a weird concept to most people. Waves are carrying momentum even before they break, but the simplest intuitive way to think about it is once a wave breaks, it's pretty clear that it's got a lot of momentum. When you get that, it's called a roller, that mass of water and foam that's more or less surfing down the front of the wave. When you're standing in a surf zone, so if this is where the waves are breaking, if you're standing in where the waves are already broken and they hit you, they tend to knock you backwards. That's the momentum of that wave getting transferred into your body. Force, that's a force pushing you backwards. And this momentum is always getting deposited into the water, where the waves are shrinking and going from their maximum size where they're breaking to zero at the shoreline, all of that momentum gets deposited into the water. This continual deposition of momentum is a force in the direction the waves are moving. The alongshore component of that force generates a current. This current, it's just generated in the surf zone and doesn't extend far outside of it. And it's usually pretty subtle. You have to really pay attention to notice it at all, because mostly what you see is just the wave motions going back and forth. By itself, it's maybe, if you average out all those wave motions, maybe 10 centimeters a second or something, wouldn't be moving any sand or gravel or boulders by itself. But the fact that the breaking wave turbulence stirs up, well, not boulders, but if it's a sandy beach, there's always plenty of suspended sediment in the water column. And that sediment is then advected alongshore. So that's the key process that's going to drive all of this. And it's always happening. Some days the waves are coming from the left, as in this schematic, and some days the waves are coming from the right. So some days the sediment's moving to the right, some days it's moving to the left. But if you add it all up over, let's say a year or longer, there'll be some net transport. And for the long-term change in coastline position and coastline shape, it's the alongshore gradients in this net transport that really matter. So if for some reason, we'll come back to what reasons there might be, you have a gradient in alongshore transport, so we think of a control volume along the shoreline. If, as I've drawn here, there's more alongshore sediment flux coming into the volume than going out, you're gaining sand over the course of years, and the shoreline is going to be accreting seaward then. Or if the gradient goes the other way, it's a long-term continual loss of sediment, and the shoreline will be eroding. All right. So the key concept that's driving all of this is the flux towards shore of a longshore momentum. And if we are to quantify this relationship between a longshore transport and flux towards shore of a longshore momentum, it might make the most sense to do that in terms of the breaking waves. That's where all the action is actually happening, and that's what the community tended to focus on. It turns out that with some simplifying assumptions, if we're talking about relatively large scales, you can alternatively characterize this flux towards shore of a longshore momentum in terms of the breaking waves or in terms of the offshore waves, before the waves do all the transformation that they do as they move into shallower and shallower water. And conceptually, it's just a lot simpler to think about things in terms of the offshore waves. So that's the step we're going to make here. It's the offshore waves. And one of the things that simplifies this is we can consider the offshore waves to be, on any given day, the same along a stretch of coastline. And in that case, the sediment flux variations along the coastline are just related to the orientation, the local orientations of the coastline. And that then gives us the gradients in transport that then reshape the surface. We'll see it also depends on the wave climate, as we'll build up in the next little while here. But the main point is that curvature of the coastline gives you coastline change. So that in the way I've drawn it here, a convex seaward section is going to be eroding, and a concave seaward section is going to be accreting. Like so. So shape of the coastline gives you patterns of flux that change the shape of the coastline. So this is that morphodynamics. It's just like dunes or ripples in a stream bed, which I used to study around here a lot, except it's bigger and on its side. All right. So next, we might want to analyze more what this relationship between shoreline orientation and a longshore sediment flux is. I've just drawn some arrows here at this point, but we can get a fair ways just thinking about the offshore waves and reasoning out what this relationship between sediment flux and relative angle between the waves, the offshore waves, and the coastline is. We can start by thinking about a couple of limits. So in one limit, these are the wave crests. So they're coming straight on shore. The angle is 0. There's no alongshore component to the force once the waves break at the shoreline. And so the sediment flux has to be 0. And if we gradually increase the angle of these offshore waves, at least qualitatively, we know we're increasing the alongshore component of the force once the waves break. So the sediment flux is going to go up. And in the opposite limit, if there's 90 degrees angle between the wave crests and the shoreline, the wave momentum and energy isn't propagating towards shore at all. And so again, 0 flux there. And if we gradually decrease that angle, the flux is going to go up. In between, neither of those limitations are all that limiting, and we're going to have a single hump to that curve, qualitatively at least. So far, so good. So this turns out to be a lot of what we need to know to understand coastline morphodynamics. We'll start out thinking about what if the wave crests are coming in at an angle relative to the overall coastline orientation that is lower than the one that maximizes the flux. So we're in this part of the curve where flux is limited by the alongshore component of the momentum. We call these low angle waves. And this is when the pattern of arrows is like I was showing you before, because if we think about going over, think of this as a very subtle low amplitude bump on an otherwise straight coastline. As we move along shore past the crest of this, the angle between the wave crests and the shoreline is increasing, which means we're coming closer to that flux maximizing angle. And so the sediment flux is increasing along shore, which is going to tend to erode the crest of this bump. And this turns out to be just a simple smoothing effect. And in fact, for the limit of very small amplitude perturbations on a straight coastline, you can derive a diffusion equation. It's the diffusion of coastline position. And it's just a simple smoothing. And that's not that interesting. But if the waves are coming from an angle that's higher than the one that maximizes the flux, now we're in that regime where the limitation is the flux towards shore of that alongshore momentum. So now moving along the shoreline at the crest of the bump, the angle between the wave crest and the shoreline is still increasing, but now that's taking us farther away from that flux maximizing angle. So in this case, the crest of the bump, control volume anywhere on there, is going to be gaining sediment, so that bump is going to be growing. And it turns out, if you do that small amplitude approximation, this is still a diffusion problem, but with a negative diffusivity. It's anti-diffusive. And that's just about as far as you can go analytically. And I'm not showing you the analytical part, but it doesn't get you much farther, because as soon as a bump, if we've got a wave climate, so some days the waves are coming from low angles on any coastline, some days they're coming from high angles. If we add up the influence of low angle and high angle waves, it turns out most coastlines are dominated by low angle waves, and they do tend to stay smooth, especially over some range of length scales, as we'll talk about. But if you're dominated by high angle waves, even just a little bit, then you can analytically say how fast those initial bumps are going to tend to grow. But as soon as they start to grow, the analysis doesn't work anymore. And to investigate the finite amplitude evolution, finite amplitude shapes and how they evolve and how different features along the coastline interact with each other, you need to go to a numerical model. So very shortly, I'm going to get to a really simple numerical model that really has just these dynamics plus something we call wave shadowing. So this is an example from the east coast of the UK, where we've got a big rocky headland that's in the wave climate that's dominated by waves coming from the North Sea. And if we're picturing being tucked on a coastline, a bit of shoreline up in the protection of that big rocky headland, most days nothing's happening, and the net sediment flux is going to be pretty small up there. But if you move down drift, that's the downstream equivalent for coastlines. Moving down drift, you're going to get exposed to more and more influence from those dominant waves. And so the net flux has just got to be increasing. So a wave shadow gradient is always going to give you a divergence of a longshore flux and erosion. And so there's these two large-scale types of interactions, the curvature-driven flux gradients that we've been talking about, plus now these wave shadow fluxes, and the two interact, it turns out. Because if we just started with a straight coastline here and turned on this wave climate, the erosion is going to tend to generate a concavity. And on those days where the waves are coming from this direction, those waves are going to be a smoothing influence. So the greater the concavity gets, the stronger the smoothing influence from the curvature-driven gradients is going to become. And at some point, this curvature becomes great enough that those two influences balance. And then you still have a erosion going on here, but the shape reaches a steady state and the erosion is just spread along shore. And that whole coastline ends up moving back together. Now, this is true not just for that, if I back up for 1 second, for the case of a big rocky headland sticking out, but also if the headlands are self-generated. And we're going to see in the next handful of slides that these and these are self-organized, spontaneous, emergent features of the dynamics, not rocky impositions from the geology, but the same interactions of wave shadows and curvatures still apply there. All right, so now moving toward the numerical model. It's a really simple model. It's just the numerical equivalent of the paper and pencil simplicity, where we've just got that top equation is just this conservation of nearshore sediment that we've been talking about, where eta is the position of the shoreline and d is the depth over which the erosion or deposition is occurring, and the gradient in a longshore sediment flux. This is one way to quantify a longshore sediment flux as a function of breaking wave height and angle. Could alternatively do it in offshore for the offshore version, but the part in brackets there, that is the flux towards shore of a longshore momentum. This is just a semi-empirical equation. It doesn't completely make physical sense. It's just been used a lot. So that's not gospel. That's just one way of characterizing the transport. That there's a bunch of different ones, but they all have really similar characteristics. So we can't have high degree of confidence quantitatively in the details of what comes out of this, just because it's sediment transport. And that's generally the case. Now, the other key part of this modeling is it turns out that you need to model a whole wave climate. It's the effect of waves coming from different directions at different times that makes a big difference. And so there's different ways of characterizing a wave climate. For what I'm going to show you, we're going to stick to the simplest way that we came up with. So in the model, waves come from a different direction each day, choosing a direction from a probability distribution function that is just determined by two parameters. U is the proportion of influence from the high angle waves. So if that's greater than 0.5, interesting things are going to happen of one sort or another. If it's less than 0.5, nothing interesting is going to happen, unless you like smoothing and straightness, but which is legitimate. The other parameter is the asymmetry. So how much influence do you have from waves from the left looking offshore versus waves from the right? And again, if that's 0.5, there's a balance and no asymmetry, and anything deviating from 0.5. So in this case, we've got symmetric but high angle dominated distribution. This one, it's not, the diffusivity for a nearly straight coastline would be 0, but with a big asymmetry, etc. All right. First example I want to show is a particularly fun one. So this is, you can see bumps start to grow initially. Over time, you see we lose some of the bumps. This is because of wave shadow interactions between different features. And so the pattern coarsens, the length scales get bigger over time, and eventually we get these flying spits developed. And the wave climate in here is just influenced by the waves that can actually get there. And so the flux is actually in the opposite direction back in there. When we initially saw the model, we didn't know what the model was going to do when we started this out. And when it did this, which happens when you've got a pretty significant asymmetry to the wave climate and high angle domination, we said, oh, that's really, really fun to watch, but silly. We won't show that to anybody. But it turns out these things are all over the place if you look for environments that have these very asymmetric, high angle dominated environments. So that's one thing the model can do under those, or this set of dynamics produce under that kind of wave climate. If the wave climate is less asymmetric, but still high angle dominated, you end up with these cuspate cape shapes, which if you wait for the right amount of time, can have the length scale that explains various cuspate cape shapes around the world, which didn't have a good explanation before that. So we've got, these are two of the things that can happen from these really simple dynamics. So there's a rich set of behaviors that come out of these really simple dynamics, and a few commonalities to a bunch of different types of patterns that come out of these dynamics. But the thing we're going to focus on a lot for the next bit here is that the shape of the coastline is a sensitive function of the wave climate. What I mean by that is, if we just think about keeping the wave climate characterization really simple with these two parameters, if we make this phase space of U and A, these are the cuspate capes in C, flying spits. The R is something Andrew Ashton, a student doing this work at the time, called recurved spits that are kind of, they don't quite sprout flying spits, but they look more asymmetric than capes. Sand waves are something that we see in a handful of places around the world. They're basically just alongshore migrating zones of accentuated erosion and accretion, but people don't notice that as much. So subtle features where the wave climate is just barely high angle dominated. All right, so the point here is that changing U and A just a little bit, even if we're within the cape field here, changes the shape. So this is just showing if we increase U a bit, the aspect ratio, the cross-shore to alongshore scales increases. Even if we change U a little bit, this changes the shape in that way. And changing the asymmetry, you can go from more or less symmetric capes, to very much less symmetric things. So On a big coastline with large scale features, this could add up to potentially a lot of coastline change if the wave climate were to be changing. Just briefly to show that this isn't limited to these kinds of coastline shapes I've been showing you, but also to convex shaped coastlines that you tend to get if your boundary conditions are open. So if you just start with a boxcar shoreline shape, the sinks of sediment on either end cause erosion. The top image shows a bunch of time slices of how that system tends to evolve. The bottom is showing an example of if you change the diffusivity, make the wave climate more diffusive, more strongly smoothing, you tend to get smaller curvatures in the darker red. And the asymmetry would just change the orientation of this whole thing. That'll come up later on, but for now, the point is these points about the shape of the coastline is a sensitive function of the wave climate, applies to basically any kind of coastline that's got sediment. Even a rocky coastline with sandy beaches in front of it has this aspect, which then brings up the changing storm climate, even if it's decadal scale oscillations in the climate, different storm climates over years or decades are going to tend to change the shape of the coastline. And potentially longer term trends related to warming could come into play as well. So then the question really is, how much are these shapes going to change and how quickly? And early on in this, we didn't have any basis for what the actual changes might be. So Jordan Slott, great grad student at the time, just did a bunch of experiments where we started with some capes that have the characteristics of the North Carolina capes. This isn't trying to model North Carolina. This is just making a coastline that has about the right aspect ratio. And then change the wave climate in various ways. So here, making it making the asymmetry go the other direction. We see we've got green shows accretion of the coastline and red is erosion. If we change the asymmetry a different way, whole different parts of the system have accretion or erosion. And this is just increasing or decreasing the high angle wave influence so that it's damping out making the aspect ratio smaller, tending to erode the capes and accrete in the bays. So lots of different things can happen depending on how the wave climate is going to shift. One of the other ways we've done this is just by saying, let's look maybe at what we think would have happened over the last century and a half when we can actually produce a hindcast of the wave climates affecting the Carolina coast. So this starts with the fact that ships started recording barometric pressures in about 1870. So we can reconstruct the pressure fields in the Atlantic back that far, and based on the pressure fields, we can derive the winds and then the waves, and then combining that with the travel times across the basin, you can convolve all this with some statistical wizardry from Fernando Mendez at the University of Cantabria into what the wave climate, what the wave conditions would have looked like on any particular day for the Carolina coast going back that far. So lots going on in this, but it starts with this. On the right is a depiction of how if we digest the wave climate into these U and A parameters, the dotted lines are the annual values and the solid lines are the decadal averaging, 10-year running average. So you can see a fair amount of shifts in U and A just related to climate oscillations in this case. This is just an exaggerated, that the axes are stretched in the cross-shore direction, but this is that coastline that shares some of the main characteristics of the Carolina coastline as a case study. And then this is showing along that coastline through time what the shoreline erosion rates or accretion rates were, where blue is accretion and red is erosion. These are 10-year running averages. So dark red is losing tens of meters of shoreline per year for a decade or so. So that's really, really, if you think about that, that's whole towns in a decade. When this big change was happening, we didn't have so many towns on the beach, but turns out we can see that this signal in the historical record of shoreline change, which then brings up we could potentially forecast into the next century based on GCM output. And this is a project we're just starting up with Fernando Mendez. It'll be past a decade or two. It'll have to be statistical forecasts rather than deterministic, but that's ongoing work. Now I'm going to focus on some work we did for a while looking at this period between something like 1980 and 2000, where you can see on here, this analysis is suggesting a fair bit of erosion on the updrift side of these capes and some accretion, at least later on in the period, on the downdrift side. And explain that more in a moment. But this was motivated by an observation from Kumar and Allen that the size of hurricane-generated waves was increasing over that time period. We thought at the time perhaps that's a warming trend, but it turns out to be part of an oscillation. But nonetheless, we had this observation that the wave climate gave us a basis for how the wave climate was changing. So looking at what directions those hurricane-generated waves came from, it turns out the main effect that that change in wave climate had was to increase the asymmetry. So you're going to, the white is the pre-wave climate change shape. We're going to tend to have rapid erosion on the updrift side of these capes and accretion on the downdrift side in response to that wave climate change. That's just a schematic sketch to get the main idea there. But, and so we did see this in the historical record for those undeveloped capes or unstabilized capes. But the heavily developed capes, none of this makes any sense. Because something we found really early on, if we're thinking about a shoreline, and again, we're just using these capes as a case study, much more general findings than that, but if we're stabilizing some part of the coastline, and this is the part of the US, well, the world really, where the technique of beach nourishment really got popular. So beach nourishment is just a stabilization effect where if your shoreline is moving landward and you've got a community to protect, seawalls or groins have lots and lots of effects that people discovered from New Jersey's experience that made them illegal. But another way to do it is just to bring in new sand, reconstruct the beach every handful of years. Usually you're dredging sand offshore and building a beach with it. And you haven't changed the background conditions that make erosion happen. So you have to repeat it every handful of years. But it has become the standard practice for shoreline stabilization in much of the world. And it kind of started along the Cape Fear coast here. So early model experiment, we just said, what if we were in this stripe, we're going to just nourish the beach. And in the model, the long-term effect of nourishment is you make sand appear at just the rate you need to keep the shoreline in the same place. So the white is the shoreline in this nourishment world. The landward edge of the white is the shoreline that's been nourished. The back end of the white is where the shoreline would have been if it weren't being nourished. So one thing we get out of this is that even local stabilization changes the behavior of the whole system. White is where we've gained land from the nourishment, and black is where we've lost it. So even one localized manipulation changes the morphodynamics of the whole system here. These towns haven't known it, but they're having to stabilize the whole flank of this cape. So to look at this in a little more detail, at one point we made the model a little more detailed in where we were adding the nourishment to try to compare to the historical records of beach nourishment volume. And this is a proxy for the monetary resources that the community and the federal government have to put in to keep the shoreline stabilized there. So the solid line are the observations of cumulative beach nourishment volume on this flank of Cape Fear. So you can see starting in the 60s, this is when basically the practice of keeping the beach where it is by nourishment got going. And the dotted line is the model cumulative beach nourishment required. The dark dotted dashed line there is the, if we didn't have wave climate change, that's just the community having to prevent the downdrift migration. Even with a constant wave climate, these capes tend to move in the downdrift direction. So the updrift flanks are erosive, and that's just the resources needed to prevent that cape from migrating. The other lines are the model where we turned on the wave climate in the mid-70s. We turned on the wave climate change based on that Komar and Allen observation. And the other lines are the model with either expanding the nourishment in a way that mimics what was actually done or not. But the point isn't how closely we can match those lines. The point is that we can't get this change in slope without the wave climate change. So this really shows that even though the coastline can't respond to wave climate change, the wave climate change signal is still in there in the human component of the system, that people are having to expend resources faster. Okay. In the longer term, I'm not going to take time to talk about decisions here, but nourishment's really expensive. Sand to nourish is getting scarce. Sea level rise is going to make all this tend to happen faster. Communities aren't necessarily always going to keep up. So this is an economic analysis that relates the long-term benefit from widening the beach. So it turns out property values can be decomposed into proximity to schools, but also and other things, including beach width. If you look at the property value data, and without going into the details, this analysis compared to the cost of nourishment can be used to define an optimal nourishment frequency, or to tell you when it becomes infeasible economically to nourish. And so in this result, bunch going on here too, but the main point is now we've got this Carolina-like coastline with communities on either side of a cape. And this is just hypothetical. What if there were higher property values on the updrift side versus the downdrift side, or vice versa? This is showing a century's worth of shoreline change with a couple 100 meters of sea level rise related erosion, which I haven't touched on, but just sea level rise tends to make the shoreline move back a lot faster than you might think. So the green line is no wave climate change and no human stabilization. Flat would just be the shape of the coastline staying the same through time. Black is without the human stabilization, but with wave climate change. This is that big updrift erosion on the updrift side of the capes showing up. And then the red is if you have a higher property value community on the updrift side of the cape, they end up being able to maintain the erosion much longer, maintain the stabilization rather, much longer than if the updrift community had lower property values where they've given up at some point. And so we've got some hundreds of meters in shoreline position over a big chunk of a cape that's different depending on the human decision making here. And that's, several rows of houses potentially. All right, there's analogous sort of linchpin locations that I'm not going to take the time to go through this in detail, but on this other kinds of coastline, there's similar dynamics between towns that they might not realize it, but if the asymmetry of the wave climate changed so that the shape of the coastline was tending to change, if your wealthier communities are in the place that's tending to erode fastest, well, let me back up. There tends to be a cascade. What this is all showing, different darknesses here are different distances from the edge. This is cumulative nourishment volume for the far end is the rate that it's being used is high at the end because that turns out they're doing a lot of the stabilization work for all the other communities without knowing it. But where that flat lines is where that community had to give up. It didn't make sense anymore economically. And then the next community has to start expending at a higher rate because the shape of the coastline passes on the higher erosion rates. So there's this cascade of failure. And the details of it depend on how the economic prosperity is distributed along the coast. Okay. Part 2. Going to be talking about cross-shore sediment fluxes and zooming in for a bit on, this is one of the stretches where that Highway 12 goes along here. The main flux that we're going to talk about here is overwash. That just happens when during a storm, wind tends to push water up against the shoreline. Wave momentum, the cross-shore component, pushes the water up against the shoreline. That can bring the waves in contact with any dunes that you've got there and tend to erode through those dunes if it lasts long enough. Or if the water levels are high enough to go right over the dunes. And in either case, you end up spreading sand back onto the highway. And this is that Highway 12 after a particular storm. This process is why those barriers are there, why those strips of sand exist. It's just because of this storm process of putting sand up onto the shoreline. And those barriers wouldn't be there if sea level weren't already also rising, but this is how they keep up with rising sea level. So in this schematic, red is some particular year and orange is some later year. And this is the case, you can see little bumps of dunes here, but somewhere in between those two times, the dunes must have gotten knocked down and a bunch of sand deposited. This will both tend to maintain the barrier at a certain minimum width and cause some shoreline erosion and cause vertical accretion. That the feedback here is that as sea level's rising, it's tending to make the island lower and narrower, which makes overwash happen more frequently. More frequent overwash, more rapid deposition. So there's going to be some, at least quasi-equilibrium height of the barrier above sea level as sea level's rising. That's in the natural state. This is a classic example from the undeveloped Outer Banks here, where this was an overwash event in the late 60s, and some more recent ones you can see some evidence for. There's a little track along here, but there's no bridges or ferries to this island, so there aren't many vehicles. It's just a track through the sand. So that's down here. The highway that connects a bunch of towns starts with a ferry terminal here, goes along the island of Ocracoke, another ferry there, and then goes and connects to the rest of the world. We're going to focus now on Ocracoke Island, where this picture is showing just after Hurricane Isabel, which made landfall right about here, looking toward that inlet. What we're seeing is the highway going to the ferry terminal at the end of the island, and it looks like the highway is just a sand track here because it got covered with sand. And this is a circling around in the small plane. You can see the highway department busily taking all that overwash sand off the road and rebuilding dunes. So the dunes are maintained much more continuously than in the natural state, and the sand is removed from part of where it's deposited. Over time, this is another, the road is basically at the back of the beach here without any place to relocate it to. And so this motivates what how do barriers evolve with this kind of human interaction with the natural processes? So for this, we used a relatively recently developed coupled model suite. This is work led largely by Laura Moore, my close collaborator, and Catherine Inardi, who did a postdoc between Laura and I. And this couples models that represent dune growth and dune erosion and overwash processes and the alongshore transport gradients that we've been talking about, as well as some human dynamics that I'm going to get to in a moment. But first, to just focus on what the model looks like in the natural when representing the natural state. So this is a plan view image where brown is higher elevation. So this is showing a dune line that's not quite continuous, and blue is water, ocean level, sea level. And this is the initial case where this model run started when a dune wasn't there. It must have just been overwashed by a big storm. And this is showing through time the overwash events happening, raising the elevation of the island, while all this time sea level is happening, is tending to make the elevation lower. Dunes develop now and then. Gaps in the dunes persist for a while, so you get heterogeneous overwash, etc. But then if we couple it with this, that one of the human dynamics modules is what happens to protect roads. So the rules for this part of the model just come from common practices and what the North Carolina Department of Transportation does. This was just last month on this stretch of the road where the Hurricane Erin, that didn't even make landfall, put some meters of sand on the road. So we're out there for the next bunch of days, moving the sand off the road to rebuild those dunes. If the beach is too close to the road, in recent decades, they've put out sandbags, which is represented in the model, and you relocate the road farther landward when the beach gets right to the road, if there's room to relocate the road. So this most recent version of this modeling is actually a participatory modeling that involves the stakeholders here. The National Park Service is part of the National Seashore, so their mandate is to try to keep this as natural as possible. The Highway Department, and especially the Village of Ocracoke, are very motivated to keep a transportation corridor there. And so we are looking at the effects of different options that are being considered there. First, let me just show you this, what happens. Let me back up for a second. The worst of these problems is in this part of the coastline, an erosion hotspot, and that's where I'm going to zoom in on just to show what happens in the model when defense of the road is successful enough that overwash doesn't happen very much. You can see the elevations getting lower and lower, and when the back of the island gets blue, that's what we call drowning. There might still be a dune there, but if there's nothing behind the dune that's above mean sea level, we call that the beginning of drowning, and the model stops. And well before that, it's actually below mean sea level. Of course, it's not usable for a road, but we're just sticking for the moment for here with that definition. So the three different options that are more or less being considered: status quo, doing what we're doing, although the Department of Transportation knows that's not viable into the future anymore, and beach nourishment for the erosion hotspot zone, which would also involve maintaining the dunes as has been done to protect the roadway, or somehow either expanding that ferry route so that it comes all the way back to the middle of the island or all the way back to the village, which the village hates because it would really make that a much longer ferry route and impact their economy. Or it could be a long bridge, has been done elsewhere on the North Carolina coast. And we do this for different sea level rise rate scenarios and for So the inputs are the initial topography. This is a synthetic histogram based on the observation of storm patterns in the area. We do 100 different runs for each management option and sea level rise scenario, and then show you some average results that are averaged over these 100 runs for each case. This is the status quo under the lowest sea level rise rate scenario, and we're not on the trajectory of carbon emissions for this to be realistic, but for this lower case, this is just showing, so this is a domain number, just that's for a longshore distance in model speak, and this is cross-shore distance. So solid line is the initial shoreline, or sorry, the shoreline at year 25, year 50, 75, 100. This is just the shoreline erosion because of gradients in longshore transport chiefly that we've seen before. The green are the shoreline moving inward from the bay side, and that's just inundation. That's just not getting enough overwash sand for that part of the island to keep up with sea level rise. So the island's getting narrower for those combined reasons. And this is showing what it looks like in this view when the island drowns, which goes to zero. This is similar for nourishment. So the shoreline on the ocean side stays put, but inundation still does its job on the sound side. And this is for the roadway alternative, i.e. we're not maintaining a roadway on the island. So we're just letting overwash happen. And you can see the shoreline's actually moving landward to maintain that minimum width in that case. Okay, that's all three of these superimposed. And this is again under the lowest sea level rise rate. So for the roadway alternative, the shoreline's in about the same place as for status quo, but the island's wider. Okay, I'm going to skip that. Higher rates of sea level rise make all of this happen faster. Just that's probably not surprising. Putting this all together, this is showing the results at 100 years under, that's the high sea level rise rate scenario. This is the intermediate and intermediate low. This is what it looks like at 100 years if the island is still there, like in these, the intermediate low scenarios. The numbers here represent the years where most of the runs drown, or 40% of the runs drown. So that's, the island, again, the island wouldn't be usable way before that, but this is when the island would disappear pretty completely. Okay, so it's a lot of fun dynamics and coupled human natural dynamics in coastal environments. And if there's still any time, I'd love to have any questions. Thank you.
Well, we have time for a few questions. Paige.
Thank you. That was a great talk. I really enjoyed it. So I think about management, and I don't feel like our states have much appetite for long-term planning like this that would involve difficult decisions. But I would imagine that insurance companies would be super interested in this. And I just wondered like how that dynamic is playing out. Are they paying any attention to this? Are they?
Yeah.
I mean, I look at that and I think there's no way I would ever insure a house along the coast of North Carolina. But yeah, I just wondered your comments on that.
The great questions, and it's two of them, or I'm going to turn it into two. So for the highway part of this, one of the things that surprised us is the Department of Transportation is thinking long-term. They say, if we're going to spend hundreds of millions of dollars, we want something that's going to last 125 years. So they wanted to see farther than 100 years. They're actively thinking that way. For the insurance part, for the houses, yes, insurance is getting harder to come by. what it looks like the effects of that will be is basically to just change the demographics, that people that have enough wealth that they don't need insurance will still be there. And there are communities like that. So that's, I don't think that one's going to change the dynamics of that system are going to change. You know, in a century from now, the coastal system won't look anything like it does now, but that might be more of an overall economic collapse. You know, right now, property values are high because of all the defense and stabilization, and that justifies the defense and stabilization. If that feedback starts to go the other way, property values dive, defense goes down, and you know, so things could change, but I don't know that insurance is going to be the trigger.
Thank you. I had a question, I guess, like, this is probably not necessarily tenable with sea levels rising, but like, is it possible that like, if you but assume everything is status quo, just not develop on the crests of the waves, of the coastal waves, and just let the waves do their thing and just sit behind the line? And considering sea levels rising, how far back do you think would to be safe in for like say 100 years or something like that?
That's a good but complex question. So if we could find a strategy that allowed the elevation of these environments to increase, like it tends to in the undeveloped state, and that's why these environments are above sea level in the first place. Like if we could just have houses that we picked up after every storm and put back down, then you'd be fine. As it is, there is no distance back from the front that is safe, because if one of the things you have to do to protect those houses is to stop, I mean, I should have said it earlier, the same processes that maintain the environment are the biggest hazards that we need to prevent if they're developed. So it's completely understandable that we have to stop storm impacts, which is stopping overwash on the short term, but that means there is no place that's safe in the 100-year time scale. It's all going to go underwater more quickly. The more successful we are at preventing storm damage, the faster we're losing the environment.
A quick question, very nice. So regarding the first part of your talk, so if I was curious whether a land scale would emerge in the steady state, given a certain, wave field, and whether your model can capture it or not.
If there is one, it's related to this is my supposition, related to the limits of how big the coastline segment is. The model suggests that there isn't an upward limit to, it's a diffusive time scale, so the development, the increasing length scale slows down over time, but it never stops. There is a length scale associated with the initial growing perturbations that this model can't catch, that's like kilometers. A couple kilometers. So this is a case where the system loses its memory of the initial wavelength completely.
One last question.
Yeah, in the first part of your talk, when you were talking about the flying spits, right? And then there was the symmetric case where you have there's tongues of sediment sort of perpendicular, right, to the coastline. But part of those seem to be sediment. Part of it seemed to be land proper, so to speak, like promontories of land. So is that to be understood as the result of a long-term process of this kind? And or should that be treated as a non-straight boundary condition for your problem, where instead of starting from a straight line, coastline, you start from something that already has a morphology or a shape?
So we certainly, at this current high sea level stand, we didn't start from a straight coastline. So not saying that starting from a straight coastline is what happened, but I don't think what you start with is remembered. That if the model results are relevant, the shape that you get out there is that quasi-equilibrium shape that the wave climate dictates, and whatever shape you started with will evolve toward that. If to the degree, so all those promontories are, in this understanding, sedimentary features fundamentally because they're formed by the sediment flux dynamics. If there's land proper there, it's just because the shoreline hasn't moved landward. So I didn't get into at that point yet. Didn't get into it here, but as the shoreline moves landward, the whole active part of the seabed is part of that system, and it's moving landward and eroding into whatever's underneath. So you can get rocks shaped like the coastline, and people might come and say, it looks like the coastline is being shaped because the rocks have that shape, but it's the other way around.
Right, our time is up. Let's thank Dr. Murray again for the wonderful talk.